Hello, welcome to the section on probabilistic classification. So far we've talked about classifiers that, given a record, U, return for us a prediction of which class the target variable lies in. And now we want to talk in this section about an extension of that idea. Instead of having a classifier that simply predicts one value, we want to think about a classifier that can make more general types of predictions. So if we have a classifier that predicts one value, we'll say call it v hat, that would be called a point classifier or a point predictor. It makes just one guess. A classifier that produces more than a single guess might, for example, produce a list of guesses or an ordered list of guesses. So it says here are the top three things. So for example, we've got a camera, it's sitting on a car, it's looking at all the things out on the street. And it says, well, that could be a pedestrian, or it could be a person riding a scooter, or it could be a person who is riding a bicycle. And those would be the best guesses that the predictor makes. It knows it's not a car, but it can't determine exactly which one of those three things it is. And it may rank those guesses. So it says most likely to be a pedestrian, second choice a scooter, third choice a bicyclist. Another possible output of a predictor or a classifier would be a probability distribution on possible targets. So with probability 0.9, it's a pedestrian. With probability 0.05, it's somebody on a scooter. With probability 0.05, it's somebody on a bicycle. These are very common. In fact, probabilistic classification is probably the most common type of classifier that people use today. We also are, of course, quite familiar with the idea of probabilistic predictions from weather forecasts. If you look at your weather app on your phone, it will tell you the chance of rain today is 10%, for example. So let's just consider a list classifier. So this is a classifier that produces an ordered list. We might call these V top, V second, and V third as its best first, second, and third best guesses for what the true Y should be, what the true V should be. And of course it may produce three guesses, it may produce a top 10, or it could be a variable number. Sometimes it will know with this very strong certainty that it's a pedestrian, and others it may have more uncertainty, and so it produces 2 or 3 or 10 guesses. And so some predictors do produce a variable number of guesses, and some predictors always produce a fixed number. And so if we're trying to evaluate such a predictor, well, we'd be obviously happiest if the true V is the first choice of the predictor, and a little bit less happy if it's the second choice, and so on. One place you very often see list predictors is in a recommendation system. So Amazon has a predictor, for example, that looks at your recent browsing history and looks at your recent purchases and tries to figure out what you're most likely to be interested in for your next purchase and show you those things. And so it will figure out your top 10 list of things you're most likely to buy or most likely be interested in and show you those. One way to make a list classifier is to use unembedding that we've seen so far. So, for example, we've used nearest neighbor unembedding to construct a classifier. We have a prediction algorithm that produces a y hat. We have a bunch of different representatives embedded in Rm, psi1 through psi k. And our predictor so far has always just returned for us the representative which is closest to y hat. But it could equally well return for us the 3 closest representatives to y hat, and those would be the 3 best predictions. And the closest one would be the top guess, the second closest one would be the second guess, and so on. So we're going to spend some time in the next few sections talking about probabilistic methods, and so we really need to start looking at probability in earnest. So this is where the co-requisite in this class of knowing about probability is going to start to come into play. We're not going to use a great deal of probability, but we will certainly use some. And so just a brief review right here of probability. Our probability distribution on our target set V, it's a function. For each element of our target set, it gives us a real number, and those real numbers have to be non-negative and add up to 1, and those are the probabilities associated with those elements of the target set V. So P of V is the probability of the value V. So for example, if the target set is rain and shine, we might have P of rain is 0.15 and P of shine is 0.85. If our predictor is predicting a probability that it will rain of 15% and a probability that it will not rain of 85%. If we have a probability distribution like this, well, we have numbered the entries in the target set V as V1 through V capital K, K categories or K classes. Well, then we've also got PVI, which is the probability of VI, we can think about as the ith entry in a probability distribution vector. And so our probability distribution assigns a number to each of those K classes, and so we've actually got K numbers which give us a K-dimensional vector. And so in vector notation we might say that P is greater than or equal to 0, and what that means is that that inequality should be interpreted element-wise. All of the entries P sub I of P as a vector are non-negative. And the fact that because this is a probability distribution, the entries have to sum up to 1, we can express that as 1 transpose P is equal to 1, where the 1 on the left there is the vector of all 1's. And so that's simply saying that the entries have to sum up to 1. So we can either think about our probability distributions as functions which map script V to the reals, or we can think about them as K-dimensional vectors. Both of those are convenient, and we will make use of both choices of notation. A probabilistic classifier produces a probability distribution P hat on V given U. So we have a classifier, it takes in the input U, and it returns for us a prediction, and instead of that prediction being y hat, an embedded value of V, or instead of it being V hat, a prediction of which class the target variable lies in, it produces as P hat. And so the hat here indicates prediction. And P hat is a probability distribution on V. So it's a number associated with each of the different classes, which informs us how likely the classifier thinks each one of the different classes is to correspond to that particular u. So we'll write this as p hat is g of u. This is capital G. So the capital G is used in the same way we used it before, in that we use little g's to indicate a predictor that's taking input x and producing an output y, and a big G to use to indicate a predictor that's unembedded, that's composed with the embedding and unembedding operations to take in an input u and produce an output v. And here, because we're dealing with probabilistic classification, we're using capital G to indicate a predictor that takes in an input u and returns for us an output which is a probability distribution on v. So when you read this, you should keep in mind that we've got something a little tricky going on here. G is a function, and it's returning a distribution which is itself a function. So we've got a function that returns a function. We can call the function, so we get p hat is g of u, and then I can take p hat and evaluate it at a particular class, vi. So I can take p hat of vi. And that would give us the probability that v is vi when the independent variable is u. Of course, I could just write that all at once. I could say g of u evaluated at vi, which I'd write as g parentheses u parentheses vi. And so here, of course, this is totally fine. We used to functions returning concrete objects such as numbers and vectors and matrices, and here we've got a function that's returning a more abstract object, which is a function. And modern programming languages such as Julia can happily do this. We've seen this already when we pass around loss functions in Julia, and so here we're going to pass around probability distributions, which are just functions. Now, in some sense, the point classifier and the probabilistic classifiers are related to each other. We can say, well, for example, a point classifier is a special case of a probabilistic classifier. It's a probabilistic classifier that's saying the probability of a particular target is 100%, and the probability of all the other classes is 0. So we could construct such a thing. We'd have p hat of v being 1 if v is v hat, and 0 otherwise. And that would be a distribution that corresponds to a 100% certainty that the guess is v hat, and 0% certainty for the others, 0% probability for the others. And typically this is not what you want, of course. Yes, it's a probabilistic classifier. You've taken a point classifier and constructed a probabilistic classifier, but you haven't gained any more information out of this. You can also go the other way. If you've got a probabilistic classifier, you can construct a point classifier. So what you do is you say, well, my probabilistic classifier gave me a probability distribution p hat. Let me look out of all of the v's for the one that's most likely, the one which maximizes p hat of v. And that would be a way of translating a probabilistic prediction into a deterministic prediction, into a very specific prediction, which is actionable. So, for example, if you have a predictor of the weather that's telling you the probability of rain, at some point you have to make that actionable. You have to decide, am I going to carry an umbrella outside or not? And so one way to do that would be to say, is it more likely that it's going to rain or that it's going to shine, that it's not going to rain? And if it's more likely that it's going to rain, then you carry your umbrella. If if it's more likely that it's going to be sunny, then you don't carry your umbrella. And of course, there are many ways of translating probability distributions into actions, and this is just one way of doing it. This particular method of translating a probabilistic prediction into a point prediction is called maximum likelihood. We look for the class that's most likely, that has highest probability. We can also generate a list classifier from a probabilistic classifier simply by giving the values sorted by probability. There are several different ways of constructing a probabilistic classifier. All of the ones that we've seen so far for point classifiers can be extended. So one can have a tree-based probabilistic classifier, which is a decision tree. It has nodes labeled by feature and threshold value, and the leaves contain distributions rather than point predictions. You can have a nearest neighbor probabilistic classifier. The way that works is then if you have a predicted, if you have a query point x, then you look for the k nearest neighbors to x, so the x of i's in your data set which are the closest to x, and then amongst those you look at the distribution of vi's that you have. So if 3 of them are true and 5 of them are false, then one would predict a probability of 3/5 for the corresponding target variable at the point x. You can also do probabilistic classifiers which are based on linear predictors or based on neural network predictors, and we will come to those shortly. So here we have a nearest neighbor classifier. We've embedded the u's in R2 to give us two-dimensional x's. Given a query point, we would look at the corresponding point in the plane, and we would like to predict either red or blue for the corresponding class. The way we do it is here we look at the k nearest neighbors of a query point. So here k has been chosen to be 8. So for any given query point, we look at the 8 nearest neighbors. Let's look at an example. So we'll have a query point, say right here, and we'll draw a circle that contains 8 neighbors, which I would guess is something like that. And then of those 8 neighbors, we will count how many of them are red and how many of them are blue, and that will give us the prediction probability distribution, the empirical distribution that we're seeing amongst the nearest 8 neighbors. And so here the colors in this plot are chosen accordingly. So if the prediction is blue 100%, red 0%, then that's this color, which is dark blue. If the prediction is red 100%, blue 0%, that's this orange color. And of course, the colors in between vary. And really we're only predicting one probability here, because once we've got a prediction probability for blue, the prediction probability for red is 1 minus the probability for blue. So now we want to consider, well, suppose we've got a probabilistic classifier or a list classifier, how are we going to evaluate how good they are? And there are several different ways of doing this. It's not quite as simple as it is for a point classifier. If we're trying to judge a list classifier, then we may look at the error rate as a function of the list rank. So, for example, we have a test data set, we have a true value of v, and we have our predictor is giving us v top, v second, and v third as its guesses, and then we ask ourselves, well, then how many of how many points in the test set did the predictor get v top to be the actual true v? And we might find that, say, 68% of the samples, the v top was actually the true v. And then we could say, well, how many of the test set points was the true value among the top two guesses? And that has to be higher than 68%, that might be 79%, and amongst the top three guesses might be 85%. And so if you want just one number, you might decide, well, I'm really concerned that it be in the top three. As long as it's in the top three, I'm happy, and in which case 85% might be a reasonable accuracy. Another way to do it might be to score the test data set. So for every data point vi in the test data set, we look at whether it was the top guess, in which case we give it 3 points, the second best guess, in which case it gets 2 points, or the third best guess, in which case it gets 1 point. And then we add up the scores over the entire test set, and that's a measure of how good a job our list classifier did. Now, to judge a probabilistic classifier, that's a reasonably subtle idea. What do we have? Well, we have a data set with u's and v's in it, and then for each one of those data points, we have a prediction p hat. And so, for each data point, we have a true value, the v, and we have a prediction, which is a probability distribution, p hat, over the set of possible v's. And one way to say whether this is a good prediction or not would be to say, let's look at the p hat that we got and see whether it gives a high probability to the actual value that happened, v. So, for example, if we've got a prediction of rain, and we look back at historical data, and we look at the predictions of rain based on the weather the day before, and we look on whether it did rain or not. Well, what we'd like to see is that on days when it rained, the probability predicted for rain was large, and on days when it didn't rain, we'd like the probability predicted for rain to be small. And if we see something like that, we might say, well, that's a good predictor. Now, we've got to make this idea formal. The most common way of formalizing this idea is to use what's called a log likelihood. So we have a data set, u1 through un, v1 through vn, and we're going to have a prediction at each of those ui's, which we'll call p hat I. It's the output of our predictor when we feed ui in, and it's a probability distribution over the v's. Now, if this were the true distribution of, so if p hat I was the true probability distribution that vi was generated according to, then we could ask ourselves, what is the probability of seeing that sequence v1 through vn? So if I is 1, the probability of getting the particular v that we got is given by evaluating p hat 1 at that particular v, which is just v1. Similarly, for I is equal to 2, we have to evaluate p hat 2 at v2. And those give us the probabilities of getting those outcomes under that distribution. If we make the probabilistic assumption that each of those data points is independent, then the probability of getting the entire data set is the product of the individual probabilities. And so the probability of seeing that entire data set under those distributions p hat 1 through p hat n is simply the product from i1 to n of p hat I evaluated at vi. So this is just a probability. It says, well, you've got some distribution, and what's the probability of getting that particular outcome? And we can look at it as, well, just the probability of getting the outcome, but we can also look at it another way and look at it as a measure of the distributions p hat 1 through p hat n. And when we do that, instead of calling it the probability of getting v's, we call it the likelihood of p hats being correct. So the likelihood is simply another name for the probability, but we call it the probability when we're looking at the probability of outcomes, and we call it the likelihood when we're talking about the likelihood of probability distributions. And so we'd like this quantity, the probability or the likelihood, to be large. And this is a fundamental measure of how well the predicted distribution matches the data. Just as in our rain versus sun example, if the probability of rain is large on days when it did rain, that's a good predictor. So we can compare two different classifiers by looking at their associated likelihoods. Which one has the largest probability value, the largest likelihood? And the one with the largest likelihood we would consider the better classifier. Now, it's actually more convenient to work with log probabilities rather than purely probabilities. Now, one reason for that is that the likelihood is a product, and when we take the log, we're going to get a sum. There are some other reasons for that as well, which we'll see. So what we work with is actually the negative log likelihood. That's simply the negative log of the probability of getting v1 through vn under our predicted distributions p hat 1 through p hat n. That's the negative log of the product of the p hat i's evaluated at the vi's, which is negative of the sum of the logs of the pi's of vi's. Now, the negative log likelihood is actually a positive quantity, and we would like it to be small. If the negative log is small, it means the probability itself is large. One of the things about this is that this is, if we just look at the log of the probabilities, then that gets smaller the more data points we have. And so we need to normalize in some way. And the way we do that is we look at the average negative log likelihood. So that's here L minus 1 on n, the sum from I is 1 to n, of the log of p hat I of vi. And this is a quantity that we can compare the effectiveness of different classifiers on different size data sets. So now we have a very nice performance metric, which is this average negative log likelihood. Now, just as we did when we were looking at loss functions, when we were looking at the square loss and the absolute loss, we asked ourselves the question, if we just looked at constant classifiers, which would be the best constant classifier which minimizes the average value of those losses? Here we have a particular performance metric, the average negative log likelihood, and we can ask ourselves the question, which is the best constant predictor, the best constant probabilistic classifier that minimizes that particular performance metric. So how is this going to work? Well, we're going to have a data set which is just v1 through vn, a bunch of classes, and we're going to look for a classifier that doesn't depend on the u's. So the u's don't even exist. All we're going to do is try to predict a distribution p hat. And that distribution p hat has to be a probability distribution on script v. So what do? We're going to choose p hat to minimize the average negative log likelihood. Minus 1 on n, the sum from I is 1 to n of the log of p hat of vi. And we can choose any distribution p hat we want. Of course, it has to be a probability distribution, so it has to be non-negative at every point v, and it has to sum to 1. Now, it turns out that the optimal constant probabilistic classifier is very nice. It's a very sensible quantity. It's actually the empirical distribution of the data. So the empirical distribution of the data, we simply count up for each v in script v the fraction of the data which are equal to that particular class. So it's simply the empirical distribution. It's simply the counts divided by the total number of data elements we have. We'll call that Q. And then the p hat that minimizes the average negative log likelihood is Q. And this is very nice. This is just like when we talked about minimizing the square loss. We found that the best constant predictor was the mean. When we talked about minimizing the absolute loss, we found that the best constant predictor is the median. Now we're predicting probabilities, and when we think about minimizing the average negative log likelihood, the best constant predictor is the empirical distribution. Now, the negative log likelihood can be computed in a particular way. So we have the negative log likelihood is minus 1 on n, the sum from I is 1 to n, of the log of p hat vi. Now each of the vi's lives in one of the classes. Now remember what the classes are. We use this notation. V is v1 up to vk. Notice those are subscripts to indicate the classes. We've got the data elements, which are v superscript I from I is 1 up to n. Now if I compute this quantity, the sum from I is 1 up to n of the log of p hat of vi, well, I can split that sum up. I can split it up into those i's for which vi is, say, v1, and then I can take the log of p hat of vi, but all of those vi's are v1, so I can just write that v1, and then I can do the next category such that vi is v2 of the log of p hat of v2, and so on, up to k categories. Sum from R over I such that vi is vk of the log of p hat of vk. So by splitting it up like this, I've just split it up into categories. Notice that this inside here, inside each of these sums, the terms don't depend on I. So I've really got just a certain number of terms that are all the same, and the number that I've got, well, it's just the number of data points for which vi is v1 in this sum, the number of data points for which vi is v2 in this sum, and so on. So when I work out this sum and taking into account the factor of n, well then the fraction of terms is q vj. That's the fraction of the terms in this sum for which vi is equal to category vj. And for each one of those terms, the quantity log p hat of vi is just log p hat of the corresponding class vj. So I end up with the sum over the categories rather than a sum over the data points. And I have that the average negative log likelihood is the sum over the categories of the empirical distribution of each of the categories times the log of the probability of that category. This quantity is called the cross entropy of p hat relative to q, where p hat is the distribution that is being evaluated, it's the distribution that's produced by the predictor, and q is the underlying true empirical distribution of the v's. We might write this as h of q p hat is equal to minus the sum from j is 1 up to k of q j log p hat j using our vector notation. There's also a related quantity when p hat and q are the same distribution, so we'll call them both p. That quantity is called h of p. That's the sum over k of pk log pk, which is negative pk log pk. That's called the entropy of a probability distribution. And both of these quantities, the cross entropy and the entropy, are very important mathematically, very important practically. They're used very widely in coding theory and in information theory and in machine learning. They're fundamental properties of probability distributions. We don't need much of the theory of that here, or in fact any of the theory of it here. We just want to be able to determine which is the p hat that minimizes the average negative log likelihood. Another way to say it is, if I've got a q, which p hat minimizes h of q p hat? Because h of q p hat, the cross entropy, is the average negative log likelihood. There's a convenient quantity to use for this, and that's called the Kullback-Leibler divergence of q and p. So we've got h of qp, we'd like to minimize that over p. But actually, instead of looking at h of qp, we're going to look at this thing called the Kullback-Leibler divergence, dkl of qp, and that's h of qp minus h of q, minus the entropy of q. This is convenient for the following reason. We want to minimize h of qp over p, but actually, well, h of qp is just dkl of qp plus h of q. If I'm minimizing this quantity over p, well, this additional term here doesn't matter because it doesn't depend on p. It just depends on q. It's just a constant. So we're just shifting the objective function in our optimization problem. This quantity, the Kullback-Leibler divergence, has a very nice property that it's non-negative. One way to think about it is that it's a measure of how similar to distributions, probability distributions p and q are. And when they are the same, well then dqp is 0. Because if we look back at our definition of entropy, h of p is the cross entropy of p with itself. And so when q is equal to p, we clearly have that the Kullback-Leibler divergence of q and p is 0. And when q and p are not equal, well then the Kullback-Leibler divergence is always non-negative. This is easy to see. If I just look at what the sum is, dkl of qp is the sum over j of qj log pj on qj. So here we're using our vector notation. Pj is simply a shorthand for p of vj. So here I've used the fact that I've subtracted one log from another, and that's simply the log of the ratio. Now the log of pj over qj has a nice bound. The log of a quantity, log, this is 1, and then the logarithm looks like that. And I can compare that with the function x minus 1. Function x minus 1 is the tangent right there, and so the log of x is less than or equal to x minus 1. This implies that this sum is greater than or equal to this sum, and this sum we can expand as being equal to the sum over j of pj minus the sum over j of qj. And both of those terms are equal to 1, and so, because both p and q are distributions, and so the overall sum adds up to 0. Hence the Kullback-Leibler divergence of p and q is greater than or equal to 0. Here we used the fact that q was non-zero when we did this division, but in fact this proof can be shown to hold even if some of the q's are equal to 0. And that tells us the best constant predictor. The best constant predictor is given by the p hat that minimizes the average negative log likelihood. The average negative log likelihood is equal to the cross entropy, and so we would like to minimize h of q p hat with respect to p hat. We can make this term 0 by setting p hat equal to q, and of course this is just a constant term, and so when p hat is q, that's the best constant predictor. Best constant predictor has probability distribution equal to the empirical distribution. The resulting cross entropy is the entropy of q. So let's summarize. A point classifier makes a single guess of v given u, whereas a probabilistic classifier guesses a probability distribution on the target set, of classes v given the u. And we judge a probabilistic classifier by its average log likelihood on test data.